Good morning, welcome back. So, the topic that remains in this chapter on renewal processes is the ensemble reward characterization. We already did time average reward, we have to look at ensemble average reward. Before we deal with general ensemble rewards, ensemble average rewards, I want to deal with the simple cases of age and duration, which constitute very simple examples of reward processes. Right. So, in this lecture we will derive the joint distribution of age and duration, all right, and we will do it for arithmetic case and non-arithmetic case separately. Okay. Now, recall that if you have a renewal process, and you fix some time t, okay, the epoch of the previous arrival is SNT and the epoch of the arrival after t is SNT plus 1, and the age is t minus NT, right. ZT is just t minus SNT, sorry, and the duration x of t is just SNT plus 1 minus SNT, which is nothing but x NT plus 1. This we already know, right. This is a definition of age and duration, that is your duration. Okay. We want the joint distribution of age and duration, right. So, remember that we did time average of age and time average of duration in the earlier, right, and I also gave a homework problem saying you go and figure out the joint using time average, figure out the joint distribution of age and duration. Actually, actually it turns out you can calculate the joint distribution of age and duration for even finite t. Okay. So, for any t you can fix a t and ask what is the probability that Z t is less than or equal to Z and x t less than or equal to x, right. This would be the joint distribution, right, and this will be not a function not only of little z and little x, this will also depend on t, right, for any finite t, and presumably as t tends to infinity you will have some steady state ensemble reward. This can be written as a expectation of indicator that z of t less than or equal to z and x of t less than or equal to x, presumably it will have some steady state limit as t tends to infinity, all right. So, we will see how it works out, okay. That is the topic of this lecture. We will treat the arithmetic case first, because arithmetic case is it is very discrete and very easy, conceptually little easier, all right. So, this is what we want. The arithmetic case, let us say span is equal to 1, okay, no loss of generality. So, what is an arithmetic process? Each renewal occurs only at multiples of some kappa, right. So, in that case the probability of having a renewal in a small interval will it is Blackwell's theorem we did already, right. So, whether you have a renewal in a small interval or not depends on whether that interval includes one of these multiples of kappa, the span, right. So, this is a in some sense you can say that arithmetic renewal process and non-arithmetic renewal process behave very differently, right. So, we will deal with the arithmetic case first. We are taking span equal to 1, okay, you can take kappa, but there is nothing to be gained, okay. So, this means that renewals occur at multiples of 1, which is integers, the only positive integers, right. Of course, we are not saying that every integer there will be a renewal, We are saying that if a renewal occurs, it will occur at an integer time, that is all that we are saying. Okay. So, we are going to take x is distributed according to PMF Px. Okay. So, what I mean is that probability that x is equal to k is Px of k, where k is a natural number, all right. This is the inter-renewal distribution. Now, for this arithmetic renewal process, we will look at age and duration taking only we can look at only just integer values, okay, because you can the whole process sort of becomes a discrete time process, right. There will be this you can actually sort of forget about continuous time. Everything in the process happens at the embedded integer points. So, here is a picture. So, this is 0, right, this could be 1 renewal, 2 may not be a renewal, 3 may be a renewal, 4, so this is 2. Seven may be a renewal and so on, all right. I put a cross when the renewal happens and nothing when put a little dot when there is no renewal, okay. So, by in the notation that we got, what is so can the age be 0? Age can be 0, right. For example, the age at 3 is 0, okay, but can the duration be 0? Duration is at least 1, right, because you are not allowing for, I mean the renewals are at least separated by 1, right, there is no PMF at 0, the mass at 0 is 0. So, duration is can take values 1, 2, 3 and age can take values 0, 1, 2, okay. And what is if age, if I tell you that the age is some number, let us say 2, what can you say about the duration? So, if I say for example, at the time 5 the age is 2, right. So, what can be the duration values will be 3 or bigger, right. So, this is that is where the distribution joint distribution lives, so to speak, okay. Clear, right. So, I am only looking at integer times t, okay. So, restricting to attention to integer times, t is also in n, okay. Now, so age, so what we are saying is that duration is at least 1 bigger than the age, correct. All right. So, now I will tell you theorem for the above arithmetic renewal process with span 1, the joint PMF of the age and duration at integer time t is given by P z t x t of I comma k is equal to Px of k for I is equal to t and k greater than t, q t minus I times Px of k for 0 less than or equal to I less than t and k greater than I, 0 otherwise. All right. So, this is the joint. So, I am looking at the joint PMF of age and duration at integer times t, and I little I is the variable corresponding to the age and little k is the variable corresponding to the duration. Okay. We are saying that this is the joint distribution. Okay. Now, I have to tell you what is this q t minus I, right. Q t is the probability of renewal at time t. Okay. So, q t minus I is the probability of renewal at t minus I. So, I should say where. Okay. Now, so this has essentially two parts, right, this joint PMF. The first, that guy P x of k for I is equal to t and k greater than t, right. Thus, that bit deals with, so when I is equal to t, right, what does that mean? I is the variable corresponding to age. What does it mean to say the age is t? Yeah, that there has been at time t, if the age is t, which that means that even the first renewal has not happened so far, correct, with me. Now, what is the, so if there has been no renewal so far, then what is the probability that my duration is equal to k? It is the probability that the first renewal occurs at k, for which the answer is P x of k, correct. Suppose I tell you there has been no renewals, what is the probability that my renewal will occur at k? My duration is k, it is the same as the probability that the renewal will occur at k, which is P x of k, which is same as the value that the first renewal instance takes value k. Okay. So, the first part of this is fairly easy to see. The second part involving this q t minus I P x of k corresponds to there already being some renewals, all right. So, if you look at, so you are looking at this part now 0 less than or equal to I less than t. So, now the age is strictly less than t, which means that there has been at least one renewal, okay, clear. And so, you are looking at age is equal to, if you go back to this picture, right, you are sitting somewhere here, let us say you are sitting at this point, okay, and you are looking at this is, so your t in this picture is 6, but you are looking at the probability that there being the probability that the age is I, right, which means that there should have been a renewal at time t minus I, correct, and what else, you want the duration to be k, right. Now, so q t minus I is the unconditional probability that there is a renewal at t minus I, and given that there is a renewal at t minus I, the probability that the next renewal interval will last for a duration k is simply P x of k, they are independent, correct. So, you get this bit, the second bit, all right. That is how this theorem comes about, all right. Now, can we characterize this q t minus I for for finite t, it is some function of t, but as t tends to infinity you should be able to characterize q t, correct. So this theorem is valid as it is, right, it is exact and it is not easy, not difficult to prove. As a corollary, we can say limit t tends to infinity p z t x t of I comma k is equal to p x of k over x bar for 0 less than or equal to I less than k. Okay. So, this is a corollary that comes from the above result. So, what is so essentially I want this, right, what is limit t tends to infinity. If you look at the first term p x of k, right. So, when I is equal to t, right, the k is greater than t, right. So, when t tends to infinity, k also tends to infinity. For the I have two terms to deal with in the theorem, right. The first is the term in green, the second is the term in purple, right, that guy. So, I am saying that the green term will go to 0 as t tends to infinity and the purple term what is the one that remains. What happens to the green term? So, you are taking t to infinity, which means I goes to infinity for the first term in green and k is greater than t. So, k also goes to infinity and what happens to p x of k as k goes to infinity? It has to go to 0, right, which is because the PMF, right. So, the first part goes to 0. What happens to the second part? You will have limit t tending to infinity q t I times p x k, all right, q t I times p x k. Now, what is limit t tends to infinity q t minus I for t fixed for I fixed. It is the probability that there is a renewal at some t minus I, right. So, what is the probability that for a arithmetic renewal process, what is the probability that there is a renewal at a particular t as t tends to infinity? What is the theorem governing this? See, the expected number of renewals in a interval is equal to delta over x bar, right, by Blackwell's theorem, but that is for non arithmetic processes. For arithmetic processes at the multiples of span, the probability of having a renewal at that multiple of a span is equal to span over x bar. I think we stated this, right, you can go back to Blackwell. So, this will simply be answer to this will be span over x bar, 1 is the span. So, you get what you want, right, p x of k over x bar. Okay. So, this is your joint distribution of this is the steady state joint distribution of duration and age. Okay. It is constant in I, as you can see, but I has to go between 0 and k minus 1. So, from this you can easily find the marginal of age and marginal of duration, okay, by marginalizing one of the random variables. So, actually this was a very simple elementary probability argument, right. The only non-trivial thing we have used in this, actually the theorem itself, as I have stated it, is a completely elementary discrete probability argument involving almost nothing that that is nothing that is advanced. The only sort of advanced things we have used is Blackwell's theorem in taking the limit in t tending to infinity. Okay.